Chapter 14, Acids and Bases, from the book Introductory Chemistry of Dr. Troll. By the end of this video, you will be able to identify common acids and bases and describe their key characteristics. Also, you will be able to identify Arrhenius acids and bases. You will be able to identify Brønsted and Lowry acids and bases and their conjugates. You'll know how to write equations for neutralization reaction, also how to write equations for the reaction of acids with metals and with metal oxides. You will learn how to use acid-base titration to determine the concentration of our known solution. Also, you will be able to determine the concentration of H3O plus and OH minus in solutions. You will be able to identify strong and weak acid and strong and weak bases. And also you will be able to find the concentration of H3O or OH from Kw. You will learn how to calculate pH or pOH from the concentration of H3O positive or hydroxide ion. And you will be able to calculate the concentration of hydronium ion or hydroxide ion from the pH or the pOH. Acids have been used in spy movies and other thrillers to dissolve the metal bars of a prison cell. When you first put a Sour Patch Kid in your mouth, it tastes sour. The taste is caused by a white powder coating, a mixture of citric acid and tartaric acid. The citric acid and the tartaric acids from a Sour Patch Kid combine with saliva in your mouth, and they will produce the H positive ions or protons. Those proton ions react with protein molecules on your tongue and give you that taste of sour. The protein molecules change shape, sending an electrical signal, a nerve impulse, to your brain that you experience as a sour taste. Now, James Bond often carries an acid-filled gold pen. Bond's pen is made of gold because gold is one of the few metals that is not dissolved by most acids. When Bond is imprisoned, he squirts some acid out of his pen and onto the iron bars of his cell. With enough acid, it would be possible to dissolve the iron bars of a prison cell, but it would take more acid than the amount that fits in a pen. Here we see a small piece of aluminum placed in hydrochloric acid, which will be dissolved away in about 10 minutes. So it takes a little bit of time to dissolve a piece of metal. Let's talk about some of the properties and samples of acids. First of all, acids have the following properties. Acids have a sour taste. Also, they dissolve many metals. And other characteristic is that turns blue litmus paper in red. So the blue litmus is an indicator of pH, and when the acid touch that blue litmus paper, it turns to red. That's indicative that the solution is acidic. An example of acid is the hydrochloric acid, or HCl. Here we can see that the white sphere is the hydrogen and the green one is chlorine. Hydrochloric acid is found in most chemistry laboratories. It is used in industry to clean metals, prepare and process foods, and refine metals ores. Hydrochloric acid is the main component of stomach acid. Also, this acid helps break down food, and it kills harmful bacteria that might enter the body through the food. Sour taste associated with indigestion is caused by stomach's hydrochloric acid refluxing up into the esophagus. Also, there are other types of acids. This one is the sulfuric acid. This one is nitric acid. As we can see, they're a little bit more complex in structure. It has 4 oxygen, a sulfur, and 2 hydrogen. This one 3 oxygen, 1 nitrogen, and a hydrogen. Sulfuric acid is the most widely produced chemical in the United States. Annually, the U.S. production of sulfuric acid exceeds 36 million tons. Sulfuric and nitric acids are commonly used in also the labs. Both of them are used in the manufacture of fertilizer, explosives, dyes, and glue. Also, the sulfuric acid is contained in most automobiles' batteries. Other example of acids are acetic acid and the basically this part here on the right side you see a carbon double bond oxygen OH is known as the carboxylic acid, and this region is the one that gave the acidic characteristic of the molecule. Okay, whenever you have this kind of, it's known as a functional group. Okay, this is the carboxylic acid, and that compound will be an acid. Acetic acid forms in improperly stored wines. The word vinegar originates from the French vin aigre, which means sour wine. Acetic acid is an example of carboxylic acid, an acid contains the COOH grouping of atoms. So here we can see the COOH, known as the carboxylic acid group. Also, these are other type of carboxylic acids, the citric acid and the malic acid. We often find a carboxylic acid in substances derived from living organisms. Other carboxylic acids include citric acid and the main acid in lemons and lime, and malic acid, an acid found in apples, grapes, and wine. The other compound that we're gonna study during this video is the bases, and some of the property of the bases are that they have a bitter taste. Also, they feel like slippery, and they turn the red litmus paper to blue. When you use the red litmus paper and it turns to the color blue, you have a basic solution. As I mentioned, the bases feel slippery. All of these consumer products contain bases. Bases feel slippery because they react with oils on your skin and form soap-like substances. Soap itself is basic, and its slippery feel is characteristic of bases. Some household cleaning solutions, such as ammonia, are also basic and have the typical slippery feel of a base. As we mentioned, the base tastes bitter, quinine and caffeine. These are two examples also of bases. Bases are less common in foods than acids because of their bitter taste. Our aversion to the taste of bases is probably an adaptation to protect us against alkaloids, organic bases found in plants. Alkaloids are often poisonous. The active components of hemlock, for example, is the alkaloid quinine, and their bitter taste warns us against eating them. Some foods contain small amounts of bases. Coffee is acidic overall, but bases present in coffee, such as caffeine, impart a bitter flavor. Okay, so that caffeine that most of all loves of the coffee is a basic compound. Okay, and that's why the bitter flavor of the coffee. That's the reason that about because of that flavor. Other basic example, we have the sodium hydroxide, potassium hydroxide, and sodium bicarbonate. The sodium hydroxide and potassium hydroxide are found in most chemistry labs also. They are used in processing petroleum and cotton and in soap and plastic manufacturing. Sodium hydroxide, sorry, is the active ingredient in products such as drainer that work to unclog drains. Sodium bicarbonate can be found in most homes as baking soda and is an active ingredient in many antacids. When taken as an antacid, sodium bicarbonate neutralizes the stomach acid, relieving heartburn and sour stomach. Now let's now look for some definitions of acid and base. The first one we're gonna learn is known as the Arrhenius definition of acids. Acid is an acid produces H positive ions or protons in aqueous solution. So any compound that could produce protons in solution, in aqueous solution, will be an acid based on the Arrhenius definition. HCl, for example, hydrochloric acid, is a covalent compound and does not contain ions. However, in water, HCl ionizes to form H positive or protons and chlorine, chlorine ions. So that's why the hydrochloric acid is known as an acid. The protons ions are highly reactive. In aqueous solution, they bond to water molecules according to this reaction. Water, H2O, they have lone pairs, and these lone pairs, they are electrons. So if you have a positive charge, those electrons may uh, attract, okay, and they will basically pull that proton to them, and then they will create the H3O positive molecule, also or ion, also known as a hydronium ion. In water, the protons ions always associated with H2O molecules. Always. You will never see an H positive in water itself. If you have H positive, will be uh, bond by water. You will have the H3O positive. So H3O positive, if you see, for example, 10 molecules of H3O positive, that means that you have 10 protons. Chemists often use H positive protons and H3O, the hydronium ion, interchangeably to refer to a hydronium ion. So basically, we talk, well, protons or H3O positive, we're talking about the same thing. In the molecular formula of an acid, we often write the ionizable hydrogen first. For example, here we write the formic acid formula HCHO2. This hydrogen is the one that is ionizable, and this one is non-ionizable hydrogen. We represent the structure of formic acid with its structural formula. That is this one. This is the structural formula of formic acid, and this hydrogen is the one that is ionizable. The structural formula indicates how the atoms are bonded together, and the molecular formula indicates the number of each type of atom. Now let's see how Arrhenius defined bases. Bases are produce OH ions in aqueous solution. So any compound that produce OH minus or hydroxide ions in solution will be classified as a base defined by Arrhenius. Sodium hydroxide is an Arrhenius base because it produces hydroxide ions in solution. Sodium hydroxide is an ionic compound and contains sodium ions and hydroxide ions. So when you dissolve the sodium hydroxide in water, it will also dissociate it. Okay, remember that the dissociation is when you separate in ions. When sodium hydroxide is added to water, it dissociates into its component ions. Molecular compounds containing a hydroxide group, such as methanol, do not dissociate in solution and therefore do not act as bases. So sometimes we're going to have compounds as this. These are known as alcohols. And even though they have an OH, but this OH is covalently bonded to the CH3, is not an ion. So that's why this is not considered a base. So, under the Arrhenius definition, acids and bases naturally combine to form water, neutralizing each other in the process. Okay, so we have here the proton and we have here the hydroxide, H positive, OH negative. When they both react, they will produce the water, and this is known as a neutralization reaction, okay, because they are producing water and water is neutral. We're going to talk a little bit later about pH. We know that the pH of water is 7, and 7 is considered neutral. So that's why this type of reaction of an acid and a base is known as a neutralization, because now you don't have acid or base by itself. They combine together to produce water in a neutral compound. Now, there's another definition that we're going to learn. Uh, we have the Arrhenius acid and base, but also the Brønsted-Lowry definition of acid-base. The Arrhenius definition of acid and bases cannot explain why some substances act as bases even though they do not contain hydroxide ions. We have some compounds that they don't have hydroxide ions, but they are considered bases. The Arrhenius definition does not apply to non-aqueous solvent. Now, the Brønsted-Lowry definition of acids and bases applies to a wider range of acid-base phenomena. The definition focuses on the transfer of protons ions in an acid-base reaction. Since a proton ion, H positive ion, is a proton, a hydrogen atom with its electron taken away, this definition focuses on the idea of a proton donor and a proton acceptor. Because we're transferring protons, one is going to give that proton. So that one is known as the proton donor. And the one that is going to accept that proton is known as the proton acceptor. So by definition, the Brønsted-Lowry definition of an acid is a proton donor and the base is a proton acceptor. In 1923, Johannes Brønsted, working in Denmark, and Thomas Lowry, working in England, developed the concept of proton transfer in acid-bases behavior independently and simultaneously. So they basically work in this concept, and they found out that this was another definition of acid and bases. So according to this definition, HCl is a Brønsted and Lowry acid because in solution it donates a proton to water. So the HCl here, we have H2O here, the HCl would donate that proton to water, and now we will have H3O positive and the ion of chlorine. So because the HCl donate this hydrogen to the water, the HCl is a Brønsted-Lowry acid. This definition more clearly accounts for what happens to the proton's ion from an acid when it is associated with water molecule to form H3O or hydronium ion. The Brønsted-Lowry definition works well with bases such as ammonium. NH3 is a base. It's a compound that is considered a base that do not inherently contain OH. This one doesn't contain OH, but still produce OH ions in solution. Why? Because NH3 is a Brønsted-Lowry base because accept a proton. So when you have ammonia in water, that ammonia is going to remove one hydrogen from water and eventually is going to produce an OH. Okay, but it was because of that transfer and because ammonia accept that hydrogen from the water. Now that ammonia is considered a base because it's a proton acceptor. So in the reaction between HCl and H2O and water, the hydrochloric acid is the proton donor and the water is the proton acceptor. So here is the acid is going to give his proton to the base, that is water, and will produce the H3O positive plus the chlorine ion. Okay. Now, in the reaction between ammonia and water, water is the proton donor and ammonia is the proton acceptor. So because ammonia is the proton acceptor, ammonia is the base, and water that will give that hydrogen is the acid. Now, listen carefully. The ammonia, when it receives that hydrogen, it will produce an NH4. And water, when release that hydrogen, will produce the OH minus. As we can see here, these arrows are going from both ways. That means that this type of reaction is in equilibrium. So it goes from left to right, but also to right, from right to left. Now, if we are going from right to left, these now are going to be the reactants, and these are going to be the products. Okay, most of the time we are going from left to right, and whatever is at the left side of this arrow, okay, the left side, these are reactants, and this will be product. But if we look for the reverse process, now we're going to looking for this arrow. The things that are in the right side, they are the reactants, and now these ones are the products. So we're looking here that this OH will produce water. So that means that it's going to receive that proton from NH4. So now OH is the conjugated base of this acid because it's receiving a hydrogen from here. And because this one is releasing that hydrogen, this one is considered an acid that comes from this base. So this is the base and this is the conjugated acid. This is the acid and this is considered the conjugated base. Okay, so this is when we have an equilibrium in type of reaction. So the base will produce a conjugated acid and the acid will produce a conjugated base. Some substances such as water can act as acids or bases, either accepting or donating a proton. Substances that can act as acid or bases are amphoteric. What happens when an equation representing Brønsted-Lowry acid-base behavior is reversed? So this is the other side as I mentioned before. Now we have here the NH4 positive and the OH. So now this will be the proton acceptor, okay? And now the NH4 is the proton donor and OH is the proton acceptor. So this will be the acid, this will be the base, because this is the base, we're going to receive the H positive to produce the water, and the NH4 is going to release that hydrogen to produce NH3, so that's why this is the acid. Now NH4 is the proton, so it's the acid, and OH is the proton acceptor, so this one is the base. What was the base NH3 has become the acid NH4 positive, and what was the acid H2O has become the base OH or hydroxide. NH3 and NH4 are often referred to as conjugated acid-base pair, two substances related to each other by the transfer of a proton. So a conjugated acid-base pair, any two substances related to each other by the transfer of a proton can be considered a conjugated acid-base pair. Here we have NH3 and NH4. That means that this one that is a base will receive a hydrogen to produce the NH4. This is the base acid pair. And now water, in this same reaction, it will donate that hydrogen, remove that hydrogen, so will be considered the acid. So this is the acid and this is the conjugated base. So the base will produce a conjugated acid and the acid will produce a conjugated base. And both of these are conjugated acid-base pair. So here we have sulfuric acid, water, and here we have the HSO4 minus and the hydronium ion. So this is the acid and this is the conjugated base. This is the base and this is the conjugated acid. Okay, so how can we identify which one is the acid and which one is the base? Because when we see the products, we see that this one lost one hydrogen from here, so this one must release that hydrogen. So the ones that donate or give that hydrogens are known as the acid. In an acid-base reaction, a base accepts a proton and becomes a conjugated acid, and the acid donates a proton and becomes a conjugated base. Now, this type of reaction, as I mentioned before, between an acid and a base are known as neutralization reactions. When an acid and a base are mixed, the protons from the acid combines with the hydroxide ion from the base to form water. In this reaction, we have hydrochloric acid reacting with potassium hydroxide. Now the OH will react with the H positive to form a H2O, and then the potassium with the chlorine to produce the potassium chlorine. Acid-base reactions generally form water and salt, an ionic compound that usually remains dissolved in the solution. The salt contains the cations from the base and the anion from the acid. The net ionic equation from many neutralization reaction is H positive plus OH producing water. Okay, remember that this one in water is dissociated, and also this one, This one is liquid, this one is dissociated, so we have potassium, potassium, chlorine, chlorine. These are spectator ions, so we cancel the potassium and the chlorine and the KCl, and we will have left the hydrogen plus the hydroxide ion to produce the water. An equation or reaction of neutralization. Now, the reaction of carbonates or bicarbonates, compounds containing CO2 minus 2 or HCO3 minus 1, with acids produces water, gases, carbon dioxide, and a salt. Okay, so when we have doing a reaction between an acid and a bicarbonate or a carbonate, this will produce water, salt as a neutralization. This is an acid and this is a base, but also will produce CO2. This kind of reaction is also called a gas evolution reaction. Now, acids react with metals in a way that causes metals to go into solution. The reaction between an acid and a metal usually produce hydrogen gas and a dissolved salt containing the metal ion. So sometimes here we have hydrochloric acid with magnesium, okay, and you can see that there's a lot of like bubbles. Those bubbles are the production of hydrogen, okay, and in solution you will find the magnesium chloride compound. Acid dissolve many metals. For example, here there is a reaction of the hydrochloric acid with magnesium producing hydrogen gas and the salt. Also, sulfuric acid with zinc would produce hydrogen and the salt of zinc, and hydrochloric acid with iron would produce also hydrogen plus the salt of iron chloride. Reactions of acid with metal oxides. Acids react with metal oxides to produce water and a dissolved salt. Hydrochloric acid reacts with potassium oxide to form water and potassium chloride. So here we have HCl and the metal of oxide, and this reaction will produce water and salt. Also, a reaction of neutralization. The products of neutralizations are basically water and salt. Hydrobromic acid reacts with magnesium oxide to form water and magnesium bromide. The same reaction, oxygen, metal oxide with an acid will produce water and the salt. Reactions of bases, they are involved in neutralization reactions and also reaction with aluminum. The most important base reactions are those in which a base neutralizes an acid. One other kind of base reaction that we cover here is the reaction of sodium hydroxide with aluminum and water. Aluminum is one of the few metals that dissolve in a base. If your household plumbing pipes were made of aluminum, it would not be safe to use sodium hydroxide, the main ingredient in many drain opening products, to unclog your drain. Fortunately, the use of aluminum pipe is forbidden in most building codes. Now, let's talk about a concept that is known as the acid-base titration. This is a way that we can quantify the amount of acid or base in a solution. Solution stoichiometry can be applied to a common laboratory procedure called a titration. In a titration, a substance in a solution of known concentration is reacted with another substance in a solution of unknown concentration. In the acid-base reaction between hydrochloric acid and sodium hydroxide, the net ionic equation is as follows. Hydrochloric acid, sodium hydroxide will produce water and salt. Okay, so what this means? This means that if we know the concentration of this and it was to determine the concentration of acid, we can use this, okay, and add acid until we produce enough water and salt, okay, and that will be basically a type of titration, acid-base titration. Let's see an example. This is a representation of an acid-base titration. Here we have H positive protons in solution. This is an acidic solution, and hydrochloric acid solution is represented by this molecular diagram. In the proton solution or acidic solution, the chlorine ions and the water molecules will not be involved in the reaction and have been omitted from the representation for clarify. Okay, so here we're not presenting the water, neither the counterion of H, that is a chlorine ion. In the OH solution, the sodium ions and the water molecule will not be involved in the reaction and have been omitted from the representation for clarity. So, in titrating this sample, we slowly add a solution of known concentration to the solution of unknown concentration in the flask. So, basically what we are saying is that here we have a sample of acid and we're doing eye titration with a solution of base, which we know the concentration of this solution. So by knowing this concentration, we can determine the unknown concentration of this solution. At the equivalence point, neither reactant is present in excess, and both are limited. So there's going to be a point where, for example, you have here 5 molecules or ions of protons, and you're dropping hydroxide ion OH. So each OH is going to react with one hydrogen. So if we add, for example, 4 hydrogens, then we're going to have 4 molecules of water, but still 1 proton. When we add another one, that is the 5th one, we're going to have just 5 molecules of water. We're not going to have OH or positive hydroxide ions or protons ions here. At that point, where we have both of them in the same amount, that is known as the equivalence point. And at that point, the number of moles of the reactants are related by reaction stoichiometry. So at this point, when we find that point, we can determine by knowing what we add here, the concentration of the solution. So here we're starting to add the hydroxide ion, and as we can see here, it reacts with the H positive and produce water. And here now we have the equivalence point where also it turns in pink. This pink is because we add an indicator that whenever there is an acid, it will be clear. So that's why here and here the indicator was clear. But whenever there's no more acid, the indicator will turn to pink. Okay, so here and at this point when it turns to pink is known as the equivalence point. That means that we have the same amount of H positive and also the hydroxide ion. As hydroxide ion is added, it reacts with and neutralizes the proton from water. At the equivalence point, the point in the titration when the number of moles of hydroxide added equals the number of moles of the proton originally in solution, the titration is complete. The equivalence point is usually signaled by an indicator, a dye whose color depends on the acidity of the solution. In most laboratory titrations, the concentration of one of the reactant solutions is unknown, and the concentration of the other is precisely known. By carefully measuring the volume of each solution required to reach the equivalence point, the concentration of the unknown solution can be determined. Let's see the following example. In this titration, sodium hydroxide is added to an HCl solution. When the sodium hydroxide and the hydrochloric acid reach stoichiometry proportions, that means that we're going to have 1 and 1 hydroxide for each moles of protons, the indicator changed to pink, signaling the equivalence point of titration. Phenolphthalein is an indicator that is colorless in acidic solution and pink in basic solution. So as we can see here, because it's clear, this solution is acidic. Once we start to release sodium hydroxide to the solution, it's going to start to form that pinkish color until you have the whole solution in pink. At this point is known as the equivalence point. Okay, that point where both uh, amount of the hydroxide and the protons are equal. That is known as the equivalence point of the titration. So let's do the following example of an acid-base titration. The titration of 10 mL of an HCl solution of unknown concentrations requires 12.54 milliliters of a 0.100 molar sodium hydroxide solution to reach the equivalence point. The question is, what is the concentration of the unknown HCl solution? So, what do we have? We have that the HCl solution is 10 mils. We have the volume of the unknown. Also, we have the volume that was used to neutralize the acid, the sample of the acid, and also the concentration of that base. We have 12.54 mils. This is the volume that was used from a solution of 0.100 molar of sodium hydroxide solution. Okay, once again, we have an unknown sample of hydrochloric acid. It was in a flask, and we start to add sodium hydroxide solution until it reached the equivalence point. And remember that we mentioned that in equivalence point we have the same amount of the acid as also the base. Okay, we have the same amount. So the question is to find the concentration of hydrochloric acid. The first thing that we need to do is to find out the balanced chemical equation. We know that hydrochloric acid is HCl, sodium hydroxide. This is a neutralization reaction, so that means that because it's an acid and a base, means that we need to produce water and a salt. We have the water here, and the salt is going to be the counter ion of hydrogen here, that is chlorine, and the sodium here for sodium hydroxide. So it's going to be sodium chloride. Okay, so this is the reaction that is taking place when we are adding the sodium hydroxide to the unknown of hydrochloric acid. Now, the solution map for this problem has two parts. The first one is that we have the volume. We have this information, the volume of sodium hydroxide. We need to change this from milliliters to liters. Remember that I told you before that the units of molarity is mole per liter. So that's why we need to change this milliliters to liters. Okay, so now that we have this in liter, we can multiply by the molarity of the sodium hydroxide and have the moles of sodium hydroxide. Okay, so we have here now the moles of sodium hydroxide obtained from the volume that we add to the unknown solution of hydrochloric acid. And now this mole of sodium hydroxide, we need to turn to moles of hydrochloric acid using the conversion factor obtained from the coefficients of the balanced chemical equation, that is 1 to 1. So now we have the moles of HCl, and we're looking for the concentration of HCl. The concentration that we know, the unit that we are using is the molarity, moles over liter. So we have now this moles, so we need the liters. But which liter? The liters of sodium hydroxide or HCl. It must be the volume of HCl. Okay, so in that way, we divide by the moles of the volume of HCl, and now we can find out the concentration of HCl. So in other words, here we have the 1 mole and 1 mole, the ratio, this the conversion factors, and also the molarity. We start with the volume of sodium hydroxide. We change the unit to liters, okay, by using the conversion factor of 1 liter is equal to 1,000 milliliter. And now that we have here, the volume, we can multiply, okay, now by the molarity. This is the molarity of sodium hydroxide, 0.100 molarity. By multiplying the volume times the molarity, we're going to have the moles of sodium hydroxide. And now we need to change from moles of sodium hydroxide to moles of HCl by using the conversion factor that we obtain from the coefficients of the chemical balance equation. And now we have here the moles of HCl. And then we divide this by the volume, okay, of the sample of HCl, that it was 10 mils. Okay, 10 milliliters was the volume of the sample of HCl. So that's why we divide these moles that were obtained from this calculation by the volume of the sample that was 10 milliliters. And this will be equal to 0.125 molar. So that's how we can obtain the molarity of the unknown, the concentration of an unknown. Okay, so we have an unknown, most of the time is an acid. We're going to do the titration with the base. We're going to add some specific volume until we reach to the equivalence point. We know that we reach the equivalence point because we're using an indicator that is known as phenolphthalein, and we mentioned before that phenolphthalein is going to be unclear when the solution has an acid, but when you neutralize all the acid, it's going to turn to pink. And at that point, when it's that very pinkish solution, you are at that point at the equivalence point. And at that point, you have added a specific volume of sodium hydroxide. And that sodium hydroxide had a specific concentration because you prepare that solution to do the titration for the acid, and that will be the concentration that you use here at this point. Okay, and this is the volume. This is the volume that you use of sodium hydroxide, and this the conversion factor obtained from the uh, chemical equation. Also, we have strong and weak acids and bases. So let's talk first about the strong acids. Hydrochloric acid, HCl, and hydrofluoric acid, HF, appears to be similar, but there is an important difference between these two acids. Hydrochloric acid is an example of a strong acid, one that completely ionizes in solution. So that means that when you add HCl to water, you're not going to see an HCl molecule in water. You're going to see that dissociation, the complete dissociation. You're going to see hydrogens, protons, and chlorides, ions. If you add, for example, 100 moles of HCl, you're going to see 100 moles of protons and 100 moles of chlorine. Okay, because it's completely ionized. It's a complete dissociation. But with HF, that is hydrofluoric acid, this one is a weak acid, a one that doesn't completely ionize in solution. So this is so weak that it can't dissociate it completely. Most of the time, it's just like maybe from 1 to 8% that will be dissociated. So that means if you add 10, for example, let's say you have 10 moles of HF in a solution, you're going to have 9 HF as molecule and 1 proton and 1 fluorine, because just one of them is going to be dissociated. It's so weak that there are so few of those molecules that will be dissociated in solution. So a strong acid, when hydrochloric acid dissolves in water, it completely ionizes into H3O positive hydronium ion and chlorine ions. The solution contains no intact HCl. Okay, so here we have HCl, the strong acid, with water, and this arrow indicates that it's a complete ionization. As a product, you're not going to see HCl, you're going to see hydronium ions and chlorine. So here we have H3O, and when you add the HCl to water, you're going to see just chlorine ions and hydronium ions. Okay, that's the only thing. You're not going to see in solution HCl because it's so strong that will be ionized completely. Let's talk about one of the properties of water. Water is about the conductivity of water. Pure water is not a good conductor of electricity because it has relatively few charged particles. Remember that basically electricity is the flow of electrons through charged particles. And because water, pure water, doesn't have a lot of those charged particles, is not a good conductor. The danger of using electrical devices such as a hair dryer while sitting in the bathtub is that that water is seldom pure and often contains dissolved ions. Okay, when you are in the bathtub, you're using, for example, soap and other things, and you are adding some charged particles to water. So that's why, and at that point, it could be really, really dangerous to use electrical devices in a bathtub. If the device were to come in contact with water, dangerously high levels of electricity could flow through the water and through your body. Pure water will not conduct electricity. The presence, for example, of ions in HCl solutions result in the conduction of electricity causing the light bulb to light. So here we have a circuit, okay, with using pure water. And as we can see here, the light is off. But if we add an amount of HCl to the water, remember that HCl is a strong acid, will be dissociated, and because it will be dissociated, it will create ions, and those ions are particles with charges, and that's help the transfer of electrons, inducing that bulb to light. Okay, so that's why when we have a solution of with ions, that will help to light that bulb. So strong electrolytes will gonna help to light that bulb. Six substances are considered strong acid in aqueous solution. These are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. Five acids in the table are monoprotic acid containing only one ionizable proton. So monoprotic means that you have just one proton and a specific monoprotic acid, that compound has just one proton, that is acid. Monoprotic, mono from one, protic from proton. Sulfuric acid is an example of a diprotic acid, H2SO4. Okay, this both of these hydrogens, they are acidics. Okay, so you can remove that hydrogen. They are ionizable. So an ionizable proton is one that becomes an H positive ion in solution. Let's talk now about the weak acid. When hydrofluoric acid dissolves in water, only a fraction of the dissolved molecules ionize into hydronium ion and in fluorine ions. The solution contains many intact hydrofluoric molecules. Here we have the HF, and as I mentioned, you add HF to a solution, you're going to have a lot of HF molecule in solution, and a few of them dissociated. Here we have four, and three of them are still HF, and just one is associated by producing hydronium and fluorine. When we have a weak acid, instead of the other arrow with pointing just to the products, we're going to have a double arrow that indicates partial ionization. Is an equilibrium. We're going to have in the system, in the solution, we're going to have HF water and also a hydronium ion and fluorine, because it's an equilibrium. Some of them are going to the side, and when you're in this side, you're going to return to the left also. Okay, so it's going to be like an equilibrium. HF producing H3O positive and fluorine, and sometimes H3 positive and fluorine producing HF and water. Okay, so it's an equilibrium between these two phases. What happened with the conductivity with weak electrolyte? What do you think? If you are producing just a few ions in solution, that means that the light is not going to be that intense with as with the strong acid when we saw with HCl, for example. Here again we have the pure water that not conduct electricity, but when we add HF, hydrofluoric acid, we can see that the light glows, but what? Very weak, dimly, okay? Because there are not a lot of particles that are charged. There are a lot of ions in solution, and that's why these are really characteristic of also the weak base. The weak base are not solutions of weak base are not really good conductors. Okay, even though they light a little bit, but for a strong light, we need to use the strong acid. Okay, so we can have more ions in solution that would help to that transfers of electrons. There are many weak acids, some organics and some inorganics. Most carboxylic acid are weak acids. Organic, remember that organic are molecules that has carbon, okay? Inorganic, all the other molecules that doesn't have a carbon. Two of the weak acids shown here are diprotic and one is triprotic. So we can see here the sulfuric acid H2SO4, carbonic acid H2CO3. Both of these are diprotic. But phosphoric acid H3PO4, this one is a triprotic. Sulfurous acid and carbonic acid are weak in both of their ionizable protons, and phosphoric acid is weak in all three of the ionizable protons. Sulfuric acid, listed with the strong acid, is a diprotic acid that is strong in its first ionizable proton but weak in its second ionizable proton. Okay, so if you have, for example, a strong acid that is a polyproton, has more than one um, ionizable proton, the first one is going to be always strong, but the other ones are going to be really, really weak. It's going to be very hard to remove those protons, the second or third, if we have some strong acid as diprotic or triprotic. So what is the concentration now of the hydronium ion in a solution? If we have, for example, a 1.5 molar of HCl, what will be the concentration of the ions of hydronium? HCl is what type of acid? It is a strong acid. So that means that because it's a strong, this is going to be completely dissociated. So that means that we're going to have the concentration of hydronium ion as 1.5 molars. Okay, because we're going to have the same number of moles as HCl as H3O positive. Okay, if we have 10 moles of HCl and we add it to water, it's completely dissociated. We're going to have 10 moles of hydronium ion and 10 moles of chlorine because we dissociate, we separate both. And because we add 10, we're going to have 10 hydrogens and 10 chlorines completely. Okay, so that's why the concentration is going to be 1.5. Now, what happens if we have a 3.0 molar concentration of HC2H3O2? This one is a weak acid, so it's going to be partial ionized. So that means that the concentration is going to be less than 3 molar because not all of this is going to be completely dissociated. It's going to be really, really lower than 3 molar, okay, because it's not a strong acid. It's not going to be dissociated completely. So if you have, for example, 10 of this acid, just one of them is going to be dissociated. So that means that the concentration is going to be really, really low as compared to the concentration of the acid per se. Now, let's talk about the strong bases. We talk about the strong and weak acids. Now is the time to talk about the bases. A strong base is one that completely dissociated in solution. The same concept as a strong acid. It is completely ionized in water, okay, in solution. Some of the most common strong bases are the ones that has hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide. All of these are strong bases. Unlike diprotic acid, which ionize into two steps, bases containing 2OH ions dissociated in one step. So that means that if we have calcium hydroxide, for example, CaOH2, when we add that to water, we're gonna have 2 hydroxide and 1 calcium, okay, as ions in the solution. So sodium hydroxide, when you add it to water, you're not gonna see any sodium hydroxide per se as a molecule. You're gonna see ions of sodium and ions on hydroxide. The same concept as we saw with strong acids. Okay, it's going to completely dissociated. If you add 10 moles of sodium hydroxide, you're going to have 10 moles of sodium ions and 10 moles of hydroxide ions. Now, what about the weak base? Weak bases, what do you think? It's going to be the same thing as the weak acids, okay? They're going to be slightly dissociated in water. So we're going to have here, for example, unlike strong bases that contains OH and dissociated water, the most common weak bases produce OH by accepting a proton from water, causing the water to form OH ions, okay? So in this case, we're going to have some of them that are going to remove that hydrogen from water and produce OH. In this equation, B is a generic for a weak base, okay? So that's basically what it means. So one of them, for example, is the ammonium, NH3. NH3, when it's dissolved in water, it partially ionizes to form NH4 positive. Okay, so when you add this to water, you're going to have a molecule of H2O around here, and one of them is going to take that hydrogen, and we're going to produce NH4 and OH, because when you remove the hydrogen from water, you have two hydrogens, you remove one, you're going to have OH, the hydroxide. And that's why this compound is a basic, it's considered a base, okay? But remember, it's just a few of them that are gonna do this type of reaction because they are weak. The other are gonna stay like NH3 in water. There are many weak bases. Most of the common weak bases are organic amines. Okay, these are the most common weak bases. We have ammonium, pyridine, ethylamine. So we have a lot of different kinds of weak bases with amines, and as you can see here, this type of arrow is a representation of a weak compound. Okay, it could be acid or it could be base. In this case, it's a weak base because we're talking about amines. Okay, so this is going to give us also a hint about the if the base or acid is strong or is weak. So let's talk now about the concentration of hydroxide ion. If we have, for example, a strong base, if we have a strong base of potassium hydroxide, if it's a strong base, it will be completely dissociated. Okay, so we're going to have, if we had 10 molar or 10 moles of potassium hydroxide, we're going to have 10 moles of potassium and 10 mole of hydroxide. So that means that at the end, we're going to have a 2.25 molar concentration of hydroxide, the same concentration as the base itself, because it's completely ionized. What about a solution of a 0.35 molars of methylamine? This one is a weak base. So that's why the concentration is going to partially ionize in water. We can't calculate the exact concentration of OH from this information, but it's going to be less than 0.35 molar by sure, because it's not completely ionized. Okay, so this basically is the important thing. When you have a strong acid or strong base, the concentration of any of the ions is going to be as the same as the concentration of the compound itself, because it's strong, acid or base. Now, for a weak acid or a weak base, this concentration is going to be lower, much lower than the concentration of the base or the weak base or the weak acid itself. Now, water has a specific property that is really interesting, because water can be, as we saw before, maybe you put attention on it, but water can work as an acid or can work as a base. Water is known as amphoteric. It can act as either an acid or a base. Even in pure water, water acts as an acid and a base with itself. This is a process that is called self-ionization. So if we have, for example, two molecules of water, one of them is going to be an acid, any of them, and the other one is going to be a base. And if this is an acid, this is going to give a proton donor, to the base, producing H3O. And this one is going to produce OH. Okay, so water itself can do this reaction known as self-ionization, where it can produce the hydronium ion and also the hydroxide. Water act as an acid and as a base, so that's why it's known also as amphoteric. Now, this occurs only to a very small extent, resulting in equal and small concentration of hydronium and OH. And a good question is why, if you have H3O, you produce this in water, is not an acid? Because it's going to be neutralized by the same amount of OH. Okay, that's the reason of why, even though you have the presence of hydronium ion or hydroxide ion in water, both of them cancel, both of them neutralize. That's why the water has a pH of 7. So for pure water, the concentration of hydronium and the concentration of OH is going to be the same. And it's known, has been determined that that concentration for pure water is equal to 1.0 times 10 to the power of minus 7 molar. And if this is the concentration of each of them, we can find a very interesting constant that is known the product constant for water, where we multiply the concentration of each of them, and this will be equal to 1.4 times 10 power of minus 14, and this is known as the product constant of water, or Kw. So the Kw is 1.0 times 10 power of minus 14. So that means that the Kw is going to be equal to the concentration of hydronium times the concentration of OH, because this product is going to be this. So this also is going to be equal to Kw. So that's another formula that we have if we need to determine the concentration of OH by knowing the concentration of hydronium ion, or if we need to determine the concentration of hydronium ion by knowing the concentration of OH. Because we know that Kw always is going to be at 25 degrees, is going to be 1.0 times 10 power of minus 14. So that's the way that we can determine one of this concentration if we know the other one, because the Kw is a known constant. So in a neutral solution, both concentrations, as I mentioned before, is equal. So let's do some examples by using the Kw in calculation. The question is, calculate the concentration of OH in the solution and determine whether the solution is acid, basic, or neutral. Okay, so if we need to know, if we need to calculate the concentration of hydroxide ion, we must know the concentration of what? Of hydronium, because remember that Kw is equal to the concentration of OH, hydroxide, times the concentration of hydronium. And we know that Kw is 1.0 times 10 power of minus 14. Okay, so that's Kw. So if we want to calculate the OH, we need to know the concentration of H3O. And here we have the concentration of hydronium, 7.5 times 10 power to power of minus 5 molar. So this is the concentration of hydronium. This is Kw. Okay, this is equal to Kw. So we know this value. We know this value, so we can determine this value. So we rearrange this. We put now the Kw, the concentration of hydronium here at this point. Okay, and then to determine this value, we need to divide both sides by 7.5 times 10 power of minus 5, and that will be equal to 1.3 times 10 to the power of minus 10 molarity. This is the concentration of OH, and this is the concentration of H3O positive. Now the question is, which one is higher, OH or H3O? Which one has a higher concentration? Is H3O. This is minus 5, this is minus 10. So this concentration is considered an acidic solution because the concentration of H3O is higher than the concentration of OH. So if both concentrations are equal, the solution is neutral. Okay, we're going to have the Kw basically. We can determine the Kw at that point when it's neutral. If the solution is acidic, the concentration of H3O is going to be higher than the concentration of OH. If we have a basic solution, the concentration of H3O is going to be lower than the concentration of OH. And in all aqueous solution, for all aqueous solution, the concentration of hydronium ion times the concentration of hydroxide is going to be equal to the Kw. The Kw is 1.0 times 10 to the power of minus 14. So, in other words, we have here we can determine the the acidity or the basicity of a solution by looking at the concentration of H3O. If the concentration of H3O is smaller, okay, basically here we have H3O is increasing, actually it's increasing here, the concentration of HCO is going to be acid. If the concentration of H3O is decreasing, it's going to be a basic. If we are looking through a OH, as we decrease the concentration of OH, it's going to be acidic. As we increase the concentration of OH, it's going to be basic. Okay, so we can determine if a solution is a basic or an acidic solution by determining the concentration of H3O or OH. Once again, if the concentration of H3O is increasing, is higher, it's going to be an acid. If it's lower, it's going to be a base. The same thing with OH. As higher the concentration of OH, this side is going to be a basic. As lower the concentration of OH is going to be an acid. And also, you can see a very interesting thing here. If you compare the concentration of OH here to the concentration of H3O here, this is when you multiply these two concentrations is going to be equal to minus 14. The same thing here, 12 minus 12 and minus 2. When you multiply these two concentrations, it's going to be equal to minus 14. Same thing here, minus 1 and minus 2, and you multiply this 2 is going to be minus 14, the Kw. Okay, so that's why Kw is really, really important. It's really a really important data that we need to know because it's going to help us to determine one concentration from the other. Now, in a more simple way, we can use a scale that is known as the pH or POH. This is a way to express acidity or basicity. If we have a pH minor to 7, lower than 7, the solution is going to be an acidic solution. If the pH is higher than 7, it's going to be a basic solution. And if the pH is equal to 7, the solution is going to be neutral. So here we have the pH scale from 0 basically to 14. 7 is the neutral one. Lower than 7, all of this pH are going to be acidic, and higher than 7, all of this pH are going to be basics. So the pH scale also is a logarithmic scale. That means that, for example, here, if we this is a representation of hydronium ion, if we basically decrease 1 unit, that means that we are increasing the concentration of H3O. Just 1 unit, increase 10 times the factor of this one. So this one was 1, here we have 10. Now if we decrease the pH here for 1 unit, we're going to increase the factor by 10. So now instead of 10, we're going to have 100. So that's why as lower the pH, higher is going to be, or strongest is going to be the acid, okay? Because that logarithmic scale is going to increase by a factor of 10 each time you lower the pH. What I'm saying here, the pH basically is a function, a logarithmical function. The pH is equal to minus log of the concentration of H3O. This is a really important equation that you may need to know how to determine the pH. The pH is equal to minus log the concentration of H3O. So calculate the pH of a solution and indicate whether the solution is acidic or basic. So here we have the concentration of H3O. We know that the pH is equal to minus log to H3O positive. So the only thing that we need to do here is substitute this value and put it right here. And with your calculator, you will need to look for the logarithm of 1.8 times 10 to the power of minus 4, and then apply the negative here. Okay, so this operation here, without the minus, this operation must be equal to minus 3.74. And then when we have this negative in the outside, it's going to turn this one positive. So that means that the pH is going to be 3.74. and this pH is lower than 7. So that means that the pH that the solution is an acidic solution. So what about if I have the pH and I need to calculate the um, concentration of hydronium ion? For this one, we have the pH is equal to 4.8. We're going to do the following equation here. We're going to use the 10 power 2 of minus pH. We're going to add the pH here, and that's what's going to give us the concentration of hydronium ion. So here we have 4.8 is going to be equal to pH equal to minus log of hydronium. We're going to now to put the negative in this side. Okay, so we're going to have the negative in this side. And now we're going to use the exponent 10, the power of 10th. So in that way, we can remove this log from here, okay, and we're going to have that the concentration of the hydronium ion is going to be 1.6 times 10 to the power of minus 5 molar. So this way we can calculate the concentration of H3O by using the pH. So just put this and using the minus, you need that's really important. You need to remember the minus. It's not just the pH. Also use the sign of negative here, pH, and then apply the power of 10 there, and you're going to have the concentration of H3O. So for the POH, here is basically the same concept or process as the pH. The POH is going to be equal to minus the log of the concentration of hydroxide. Okay, so this is a specific formula. Whatever we have a POH or pH minus log of H or minus log of OH. Okay, so to calculate the POH of the solution indicates if it's basic or acidic. We have here the concentration of OH. So we just need to apply this to the equation. Substitute this value inside here. So the solution basically minus log of the concentration of OH. We're going to now put this inside here. We're going to have there the concentration, the minus log of 1.8 times 10 to the minus 4. And now we can apply the logarithm to this value. It's going to be minus 3.74. This minus will turn this to positive, and we're going to have a POH of 3.74. Now, this is another equation that's going to help you. It's going to be pretty more fast to determine about the pH, the relationship between pH and POH. So pH plus POH is going to be always equals to 14. Okay, pH plus POH is going to be equal to 14. So if this is the POH, we can put this POH here, substitute the POH in this point, and we can calculate the pH. 14 minus 3.74 is equal to the pH of 10.26. So because the pH is higher than 7, the solution is a basic solution. Okay, so if we know the POH by using this equation, we can change that POH to pH, and using the concept of the scale of pH, we can determine the acidity or basicity of a solution. And what about to determine the concentration of OH? As the same way you have the concentration of H3O, we're going to use the 10 minus POH, in this case, to determine the concentration of OH. So if we have a POH here, we can calculate the OH solution by with the POH. You need to use this 4.80 and put it here and solve for that equation. So we have here the 4.8 equal to minus log of the concentration of hydroxide. Return the minus to the other side. And when we have minus 4.8 equals to the log of OH. And now we apply the 10th power. So we can have here that the 10 minus 4.80, okay, this is going to be equal to 1.6 times 10 minus 5 molar. Okay, and this will going to be equal to the concentration of OH. So just put this value here, and you're going to find out the concentration of OH. And to determine the concentration of H3O, we just use the Kw. Now this one is concentration, it's no pH or POH. When we are talking about pH and POH, pH plus POH is equal to 14. When we are talking about the concentration of H3O positive times the concentration of hydroxide is going to be equal to 1.0 times 10 to minus 14, and this is equal to Kw. So when we use this equation, we can find out that the concentration of the hydronium ion is 6.25 times 10 power of minus 10, and this is going to be lower than the concentration of OH. So that means that the solution is a basic solution. There is another concept that is known as the buffers. The buffers are solutions that we need to create to resist pH changes. Buffers contain significant amounts of both a weak acid and its conjugated base. So you can create these buffers by using weak acids and conjugated base. The weak acid neutralizes any added bases, while the conjugated base neutralizes added acid. Okay, and this is important. Why this is important? Because the human blood by itself is a buffer. In healthy individuals, the blood pH is between 7.36 and 7.4. That is the range where the pH needs to keep in healthy individuals, okay, in the blood. If the blood pH were dropped below 7 or rise above 7.8, that would result. Okay, so that's why it's really important to keep that pH between 7.36 and 7.4. And blood has these buffers that resist any change to protect us to avoid this kind of situation where the pH will drop below 7 or increase more than 7.8 and will be detrimental to our health. Example of a buffer solution is using the weak acid as acetic acid, and also the conjugated base that will be sodium acetate buffer, acetate by itself. Okay, so we have here the weak acid, the acetic acid, and its conjugated base that is the sodium acetate. So these both can create a buffer. So in this type of buffer, when we add a base, which is going to react, this is a base, so it's going to react with whom? With the acetic acid, because you add a base. So that's why if you have sodium hydroxide, this will react with the acid, acetic acid, and will produce water and salt. And what about if we add an acid? With which of both is going to react? It's going to react with the base, that is sodium acetate. So in this case, when you add an acid to the buffer, it's going to react just with the base, even though you're going to have acetic acid as well as here. You have both. You have the acetic acid and the sodium acetate. But because you're adding a base, this base is going to react with the acid, not with the weak, with the conjugated base, even though is there because it's a buffer. You need to have present both of them, as well as here. In this system, you have the acetic acid and the acetate, sodium acetate. So you have both. But because you're adding the acid, it's going to react just with the part of that buffer that is a base, that is in this case is sodium acetate. So when you react acid with base, you're going to produce the acetate, acetic acid, and the salt. So you're going to neutralize this strong acid to a weak acid and a salt. So that's how the buffer works. In other words, here we have, for example, as I mentioned, we have the acetic acid here, and we have the acetate. So if we add a proton, we add an acid, it's going to react with the base. And if we add a base, it's going to react with the acid, the weak acid that is the acetic acid. Okay, so this is basically a figure that hopefully helps a little bit to understand more. Once again, you have both of them. The buffer have both of them, the acetate and the acetic acid. The acetate and the acetic acid. Which of them is going to react? It is going to depend on what you're adding to the solution. Here you're adding an acid, so it's going to react with the part of the buffer that is the base, that is the acetate, the conjugated base. When you add a base to the solution, where in the solution you have a weak acid and a base, this base is not going to react with another base. The base is going to react with the acid, with the weak acid, that is the acetic acid. And by doing this, you're going to resist the drastic change of pH that could result if you had this buffer in the system. So to summarize the chapter 14, acids have a sour taste, they dissolve metals, bases have a bitter taste, and they feel slippery. Arrhenius definition for acids: the acids produce protons in solution, the bases produce hydroxides in solution. The Brønsted-Lowry definition: the acids are proton donators, while the bases accept protons. Those are the definition for acid and bases by Arrhenius and Brønsted-Lowry. Also, reaction of acid and bases, they are called neutralization reactions. Uh, Acid can react with metals and also with metal oxides. And we also talk about the acid-base titration. We mentioned some characteristics of strong and weak acids and bases. We also learn about the self-ionization of water and also the Kw, okay, the constant of water. And also we talk about the pH and pOH scales, and at the end we learn about the buffers. So this is all with chapter 14, the acids and bases, by of the introductory chemistry by Dr. Traw.